So Vincent Lanticq completed his PhD at Telecom Paris and his engineer studies at Institut d'Optique Graduate School in Paris. He gave several talks in international congress and published scientific articles in journals such as Measurement Science and Technology or Optics Letters. He also taught topic in optical sensing technology. His research interests are nonlinear optic and distributed optic fiber sensing. Vincent entered Semantis, a sensors industry company, in 2009, where he started to develop sensing solution and managed a technical team that grew from 2 people to 10 people within 5 years. Vincent left the company in 2014 in the aim of designing the first technical drawings of Febus G1 system and was co-founder of Febus Optics company in 2015. So now let's go to the lecture of Vincent. It is entitled Fiber Optics, an adaptable and cost-effective technology for monitoring geothermal reservoirs at different scales. So you can, it's up to you.
Thank you, Christophe. Does everybody see my screen? Okay.
Yeah.
Okay, thanks. So thank you for the introduction. So I won't introduce myself any further. So just I will introduce Febus Optics. So we were founded in 2015, such as Christophe said, and we are a manufacturer of distributed optical fiber sensing system. We are based in France, in Pau, and we are putting a lot of efforts in our R&D and in the quality of our equipment, because to prove that we have been certified ISO 9001 last year. So we are several facilities. In France, we have 2, both in Pau, our headquarters, and our test center. I will detail this a bit further. And we have commercial antennas in Paris, Tunis, and Houston and Middle East. And we have a geophysics antenna in Strasbourg with 2 people. Here are a couple of field of work of Febus Optics. Some places where our devices have been deployed, and some of our customers. It's not the place here to detail that, but it's just an overview. So the technology we are providing is called distributed optical fiber sensing, or briefly distributed sensing. So basically we are providing those boxes. So here is a typical box. So it's a rack, an optoelectronic system, and this box is launching a pulse along an optical fiber, which is always inside a fiber optic cable. So this pulse of light is propagating through the fiber optic, and along its propagation, a small amount of the light is lost and go back to the device, propagating backwards here. And this light, we will analyze it to recover information on acoustics, on temperature, and strain. One of the good properties of distributed sensing is you can locate your measurement very accurately, because you know perfectly the velocity, speed of light inside the fiber optics here. So if this light has been created at one location, you will receive it here at one time. So that's the way you locate your measurement. Then it's such as you have plenty of sensors along the cable, typically 10,000 of sensors of temperature, strain, and acoustics along the fiber from start to end. So this offers a lot of possibilities in terms of applications. globally monitoring of infrastructure, such as landslide detection, settlement detection, leaks, fire detection, or railway or road traffic. A lot of applications are imported from oil and gas for pipelines and subsea umbilical risers and flow lines. For third-party intrusion, meaning anchors or damages on the infrastructure, ground movement, shock detection, of course, perimeter security, because you're running acoustics, so you can hear the things, so you can detect intruders. Power cables on marine renewable energies for fault detection on electrical cables, real-time thermal rating, detection of suspension of the cable, like what we call free span, or electrical events such as partial discharges. And then, last but not least, for today, is geophysics and wells. So we can do passive and active seismic. We can do temperature profiling. We can do vertical seismic profiling with active seismics, and production profiling as well. Just one slide to give you an overview of our test center. It's called CESG for Centre d'Essai Sophie Germain. It's in Pau. It's a place to test and demonstrate the distributed sensing solution in real life, meaning we have tools to reproduce ground movement, leaks on pipes, tension, bending, or whatever. And this is a very, very nice tool for us to test all the technology in real condition, or let's say fairly representative conditions. So now I will start the techniques. I will present first the fiber optics and all the technologies associated, then measurement, and then I will focus on wells, and I will conclude on what Febus Optics performs in the MIT project. So fiber optics, or optical fiber, you can call it. It's a silica bar, very thin, like thinner than a hair, very pure, and it's manufactured by vapor deposition with dopants, meaning it's not pure silica here. It's doped with dioxide of germanium, fluorine, and many other dopants. It's particular molecules, and they are used to radially vary the optical index profile. That's how we make the guiding properties on of an optical fiber. Indeed, the optical fiber is composed by an optical core and an optical cladding. The light is propagating into the optical core, and the optical cladding acts as a barrier for the light. And this optical device, core and cladding, is surrounded by a plastic coating, and this plastic coating can vary. The composition can vary, and it's depending on the conditions of usage. You can use, as a standard, it is acrylate, which is a very soft and smooth plastic. But alternatively, it can be polyimide, which is in much thinner layers and with a huge hardness compared to the acrylate. This is for when you need fairly high temperature. And you can use carbon. The carbon coating will act as a chemical barrier, and we will discuss this further. Aluminum, gold, or copper coating can be used here in order to endure very high temperature, up to 700 degrees in certain applications. So as I said, first you will manufacture a preform of the fiber. What is a preform? A preform is, let's say, a mock-up of the fiber, but very large. So it's like if you have an optical fiber, but instead of being 100 microns diameter fiber, it's like 1 meter diameter fiber. So you put this preform on the top of what we call a tower, and then with an oven, you will reduce homothetically the size of the preform to get a fiber. And then you have this fiber, we have the same parameters of the preform, but at a much smaller scale. And then you control the optical diameter, you put the coating, you control the OD of the coating, you control the speed of everything, and then you have the final code. And this is optical fiber as you can buy it in the market. So we start with the preform and we finish with a 125 microns hair here, cold into this drum. So there are different types of optical fibers, barely 2 types, multi-mode fibers for short distance and single mode fibers. So here on the top of this figure, you have a large core multi-mode fiber. And then you can consider your fiber as, let's say, a tube with a wall. The wall is the cladding, the tube is the core. And then it's like you play snooker with rays of lights. And then you have here this reflection, total internal reflection guiding the light. But then as a consequence, the ray going straight here arrive on the target earlier than the ray going left and right here. So this is a multi-mode fiber, step index multi-mode fiber. But life is better than that. Engineers have designed gradient index multi-mode fibers. So then the light is not going straight, but it's curved. And then at the end, everybody arrives at the same time, and you have not this, what we call dispersion here. And moreover, the second type is single mode fiber. Then the light is trapped into 10 micron core here. And there is only one mode. That's why we call it single mode. And this mode is going straight to the point. So there is no modal dispersion because there is only one mode. So basically, I won't bother you with this map here, but single mode is when you have one mode, but basically in such a system, core cladding, you have several modes. And then just remember, a fiber is single mode for one wavelength. If you vary the wavelengths, especially the smaller the wavelengths, the more chance you have to be multi-mode. Okay, now we have seen what is an optical fiber. It's basically like a hair of 125 micron, but this hair, you have to protect it. So you will put this hair into a cable, a composite cable. And it's always the case. You will never deploy for any reason just a fiber, maybe except on the lab, but in the field is impossible. So you put this in a cable, and the goal of the cable is to protect the fiber from unexpected or unwanted environmental conditions. But still, if you want to be sensitive to something, you have to do some trade-off on this. So it's dependent on application, communication or measurement, for example. For measurement, you will enhance the coupling. For communication, you will enhance the protection, because what matters is what's going inside the fiber, the message, the communication. And it will depend on external condition. You won't use the same cable for high pressure, high temperature condition if the cable is submitted to shocks, to tension, to crush, to rodents, for example. We never underestimate the rodents, mouses and rats can be very, very hungry seeing some cables around. So we have to protect the cable. So here, the dots, this is a cross section. The dots are optical fibers. They are on tubes. The green parts, they are tubes and gel-filled tubes. The gel have a double, let's say, role here. The first is to protect from mechanics, smoothing the mechanics, and the second is to protect from water, because fiber, they basically don't like the water, that you can oxidate your fiber with water. A strength element here in the center, something, let's say, carrying the fiber, taking all the strengths and together with reinforcement here in the outside, a humidity protection around, something trapping the water at first stage, and a sheath, barely plastic, and the plastic can be dependent on the condition. For example, you will use polypropylene if you're going higher temperature. So here, several kinds of telecommunication dedicated cables. This is a multi-tube cable. This is a single tube cable with a ribbon of fiber inside. So several fibers, let's say, agglomerated as a ribbon. And here you have several tubes with ribbons inside. You can see we are far away from just a fiber with those cables. Then, as I said, protect the cable is one thing for telecommunication, but protect the cable from harsh environments, such as you can face inside wells, for example. It's another issue. So for oil and geothermal wells, you will have high temperature or extremely high temperature, but basically 150 degree, can be a target. High pressure, hydrostatic pressure is barely more than 100 bars, and it can go up to 2,000 bars. You will have corrosion because of sea salt, because of H2S or chloride. You can have hydrogen, dehydrogen, and the hydrogen is particularly dangerous for fibers because it's darkening the fibers. There is no transmission at all at the end if you put standard fibers into dehydrogen several days or months. If you are grounded, so then you will face rodents. I already said that in the last slide. You can have other chemicals if you have if you are in a chemical plant, for example. And on nuclear environments, then you will have gamma rays, so you will need very specific fiber. So here you have some fibers, specialty fibers designed for wells. And what you can see, there is a, let's say, a common part for all of them is this fiber in metal tube. So there is a metal tube with a fiber inside, and this is called FIMT. You can see here polypropylene and metal tube and another metal tube. And you can see here several metal tubes with several metals. This is for to fight against thermal expansion of the cable. A little focus on hydrogen darkening. So here you see the reason. So the silica has two absorption peaks, one for dihydrogen here and one for OH ions here. And this actually is the the wavelengths, all the wavelengths you want to use for telecommunication. For sensing, we will use 1550 nanometer here. But you can see even if those peaks are far away from 1550, they have an effect at 1550. And you can see if you use special fiber to lower those peaks and those effects, such as blue, black, and ultimately green, you will lower the effect as well at 1550. And this is performed mainly by carbon coating. So for all well application, we will use carbon coated fibers to protect from corrosion, from water, and from hydrogen. Then we have seen how to protect the fiber, but sometimes you want to couple the fiber because you want to measure something. So if you want to measure something which is outside, and if you want this outside to be visible inside, then you need to think about coupling outside with the inside. And this is done by the cable. So you have to think about the cable composition. So one can use a tight buffered structure. Tight buffered means everything here is glued all together, or let's say attached all together. So you have a plastic here, the 4, the 3 you have a metal tube, the 2 you have glue actually, or something hard, and 1 you have the optical fiber. So the optical fiber is linked mechanically with the outside. But thing is, if you do such a thing, you will reduce the lifetime of the cable because all those mechanics will may have an impact on the fiber and may damage it. So it's fragile structure, this one. But can be mandatory. If you want to measure static strain, it's the only option. So you have to design such a thing, but thinking about thermal expansion, protection against corrosion, and all the things. This is the way of doing high coupled fibers. Now, the extreme opposite, you can do a very weak coupling. Can be enough actually for acoustics, for example. You can play with this kind of fiber. So here you can see the fibers inside in a metal tube with gel or not, and plastics and reinforcement with metal wires, and again plastic. So here you have no chance to feel something static coming from the outside because the coupling is very weak. But something very small, you can sense it because of the friction here. Even with the gel, you have a part of the, let's say, higher frequency, meaning 1 Hertz, 2 Hertz, 5 Hertz, 100 Hertz, will enter here from the outside to the inside. Then you will choose to add excess fiber length, EFL. This is a percentage of excess of fiber compared to the length of the cable, meaning from 1 kilometer of fiber, you will have 5 meters of fiber in excess. Or so, sorry, for 1 kilometer of cable, you will have 1 kilometer and 5 meters of fiber, meaning the fiber can here successfully endure an extension of 5 meters due to temperature, due to tension, mechanicals, or anything else. And with reinforcement, you can fight against crush, impact as well. So let's say to finish with the fiber optics ecosystem, just note there are connectors to, let's say, connect two fibers one to the other. You have the possibility of playing with connectors, but there is also for field application, you will, let's say, I will say sometimes, but often use fiber optic splice. So here you have this little machine. You put one fiber on one side, one fiber on the other, and then you fuse the fiber. And so you have one single fiber at the end. Yeah, well, of course, you have to protect it, but at the end, it's such as you have one single fiber. And it's much more robust. And it's put this in boxes. And those boxes is this type of box. You can see it in the street. It's for fiber to the home, for example, for your internet access with fiber. The people doing the cabling outside or the wiring, they are using these fiber optics splice trays here you have, and this encapsulation. Of course, if you do such a splice into a well, you will have to use special splice because you have special fibers. You have to use special protecting sleeves here to, let's say, maintain the splice along high variation of temperature, and use specific encapsulation with metallic things such as the one you can see here. So now, finally, let's go to distributed optical fiber sensing. How to use those cables, those fibers connected to the device to sense, to measure something. So, as I said before, we are analyzing this light here in green propagating backwards. So when this light is generated, it has some properties. So here you have the frequency, the spectrum, the composition of the spectrum of the light, the spectral density of the light. So let's say we send one unique wavelength, so it's this wavelength here in the center, then the backscatter light will have this spectrum. A part of the light is called Rayleigh, another part is called Brillouin, and another part is called Raman. The Raman part is intensity sensitive to temperature, so in temperature only. So it will, the Raman backscattering can be used for distributed temperature sensing. The Brillouin part here will be sensitive to temperature and strain. So it's the only way of measuring static strain, but it can be used as well to measure temperature. And if you want to measure one and kill the other, then you have to use maybe two cables, for example, one tight, one loose. And the third part is the Rayleigh part. So it's at the same wavelength as the incident light. And this will be coherent, meaning we can do interference with this light and we can measure the acoustics. So it's distributed acoustic sensing. So here we have the three: distributed temperature sensing, distributed strain sensing, and distributed acoustic sensing. So this is barely commercial. Febus is offering three. So G series is Brillouin, A series is acoustics, and T series is Raman temperature. So let's start with the easiest. So Raman temperature measurement. So it's very, very often used to monitor well during production, or just for temperature profile. You run a fiber down your well, and then you have this vertical temperature profile. So here you have an example. So this is a well, and these are temperature profiles measured. This is a CO2 storage well, actually. And here you have the temperature profiles before injection and after several stages of injection, and here during production. So what you have to have in mind, it's a very well resolved temperature. So you can achieve repeatability of the temperature, meaning very accuracy. It's not the same, but accuracy between successive measurements is about 0.01 degree, which is very, very low change. but it is an intensity measurement, so it has to be referenced. So you need to be very accurate, or that accurate, you need to have one temperature at the top of the well and one at the bottom. So it's better to couple this measurement with a bottom measurement of temperature. Another way to measure, another principle is the brilliant temperature. So it's G1 at Febus. And then you will track a frequency. So sometimes it's easier to track frequency because you have this property of being insensitive to losses, meaning you have a connection and then you disconnect because you are going to do maintenance on your system, or you have to disconnect because I don't know, you have work to do on the well, and then you reconnect 1 month, 1 year, 10 years later, and then the frequency hasn't moved. Maybe yes, but not the frequency. And this frequency is the one which is sensitive to temperature and strain epsilon here. So that's the good property of brilliant sensing compared to Raman. It's a little less sensitive to temperature, or a little less repeatable. It's much more 0.1 degree, yeah, which is quite a good performance, but sometimes in wells, you want to be more accurate than that. And for strain measurement, it's very accurate. It's 2 microns per meter, meaning it's elongation. So you have 1 meter here of cable, you pull off 1 micron, or 2 micron, you can see it. And you can do one measurement. Let's say I say it's static, but you can go at let's say 10 hertz up to 15 hertz frequency. So here you have a measurement, typical distributed strain measurement. So you have strain here, time here, distance here, and we play here with this bar, you see. And when we play with this bar, so the bar is oscillating, and we can see it at 1 point because it's just 1 point we are attached to the bar. Of course, you can measure temperature with Brillouin, and the good property is you can go higher range than Raman. So that's why most of the time the Brillouin is used to measure temperature over very, very long distance, such as on pipelines, for example, or flow lines. And then you will have this spatial resolution. So this is an important parameter. Spatial resolution is, let's say, the spatial accuracy of your measurement. So you will measure independently 10 meters here and then 10 meters after. So you can go down to 1 meter with all the devices, but if you go very long range, you will have to take higher spatial resolution. And you can see here, even at 100 kilometers, you can achieve 0.4 degree of accuracy. Then the coupling is quite important for Brillouin measurement, because if you want everything to be transferred to the structure, you will use that. And if you want nothing to be transferred, you will use that. And then if you want to have, let's say, the strain independently from temperature, then you will use both, and you will use this one to compensate the measurement of strain of this one from temperature. So here you have the strain measured on the cable on the top, compensated by the measurement on the one on the bottom. Finally, distributed acoustic sensing. This is a very key tool for wells, actually, because you can have an acoustic profile all along the fiber, or a seismic profile if your fiber is coupled. So here you have an earthquake detected by distributed acoustic sensing. So here you have the distance, and here you have the time. And you can see the P wave and the S wave very distinctly, but still you are sensitive to temperature because the fiber is thermally expanding, and you are very sensitive as well. This black here ray is a temperature change. It's a temperature decrease during measurement, because here the unit measured is strain rate, meaning the derivative of the strain, elongation, a long time. So how does it work? Acoustic sensing. It's quite simple to understand, but quite hard to put in place. So you have the box, and then here, at the time where this green wave is created, you have a vibration. And we can measure this variation as a phase difference in the optical light. And this phase difference is linked to the strain, or the strain rate we want to measure. And so the goal of the DAS, the unit, which is here, is to measure this phase difference. So for that, we will use a phase difference between one point and another point of the fiber successively during propagation. And this difference in distance is called gauge length. And this is adaptable. And this is important parameter because this will fix the minimal seismic wavelengths you will be able to resolve. So we have this formula still here, and then the DAS is acquiring a lot of data. So you will have one measurement each, let's say 0.1 millisecond, but in one measurement you have all the distance. And even if you want to achieve a gauge length of 10 meters, you will oversample a lot. So it's typically 40 centimeters. So if you have, let's say 10 kilometers, it's like 25,000 points here per, if you have 10 kilohertz, it's 10,000 points per second. So meaning it's 250 millions of points per second to analyze, or if you want to take the raw data to store. So there is a problem of storage with this device. So one of the main difficulties is to process the data on the fly or store the data in a long time, especially if you're running passive seismic and you don't know when the event occurred, you want to monitor, so you want to store everything. So how to use all of this for wells? I will accelerate a bit. So one main application is active seismic. So active seismic, you deploy the fiber in the well, so inside the well or outside the casing. The coupling will be better if you are cemented, for example, for sure. And then you will have a source with providing a signal here, vibrating the ground, for example, and then you will sense what happens on the well. Usually it's done by geophone, but with geophones you have, let's say, 10 or 50 geophones, and then you have to move the geophones to have all the line. With fiber, the good property is you have one single line for all the survey, and then you vibrate the ground several times, and then typically 20 to 100, and then you have your vertical seismic profiling. This is the distance, and this is the time, and this is correlated in stacked signal. So it's pulse response here of the ground. So you can see here the first arrival and a lot of tube waves, of course, because we are inside the well in that case. And then you can do it moving the source. It's like offset 1, the source is at 300 meters, for example. Offset 2 is at 500, and then you can see the distance between the first arrival and the S wave here in the middle of the tubes can vary. And then you can have standard VSP analysis to, let's say, process the data, and afterwards it can be inversion on geological surveys. Another way to use distributed sensing in wells is production logging. So if you have all those tools, mainly temperature sensing, distributed temperature sensing, and distributed acoustic sensing, then you can merge these data with different data, but let's say more classic data, such as here the casing geometry, the well, the formation here, composition, the depths, one pressure you have measured, maybe it's measured by a logging previously, depth control, which have been done maybe with the wireline performing the optical measurement, and many logging data you have measured previously with real-time fiber optic monitoring data. Here you have temperature profile, so you can see from 0, it's cold in the surface, to 120, for example. And then you can do the difference between a baseline or the difference between the last measurement. And then you can couple this DTS with DAS measurement. So this is DAS energy measured a long time. So time is the x-axis, depth is the y-axis, and it's integrated from 0 Hertz to 5 Hertz. So it's energy band, classical data. And you can see there is a correlation between temperature, between here structure of the well. You can see here a barrier of noise on the DAS data. You can see something on the temperature. The same on the bottom. You have this event here propagating here when you see the temperature, and you can see it as well on the temperature difference. So this gives to engineers, well engineers, a lot of information on production. So now to conclude, I will focus what Febus is performing during mid-project, and especially on the well called EPS1, which is a electricity geothermal as well. So we have done actually 2 deployments in this well. It was not expected. We expect to do only 1, but we had issues to face. First attempt in 2018 was quite, let's say, optimistic. So we tried to deploy a very sensitive cable, very small. It's 1.2 millimeter diameter cable here. It's a fiber in metal tube, but couple. You can see here 3 fibers. They are, let's say, squeezed by the tube during the manufacturing. And this sensitive cable, it's carried by a slick line, standard metallic slick line, and it's linked to the slick line by magnetic shuttles. Why magnetic shuttles? To couple the sensitive cable with the slick line, but as well with the casing. That's the reason of the magnets. So here you can see the real shuttles, and the magnets are here. So that could have been a nice shot. Unfortunately, it's very difficult on a long distance to handle the 2 cables at the same time. And so we failed to go deeper than 700 meters, which is, let's say, not too bad for such an innovation, because these shuttles and nothing was, let's say, validated in real life, in real well. So we succeed to descend up to 700 meters. But we have seen, because we have Brillouin monitoring, so we are sensitive to temperature and strain. So here you have your temperature gradient, but you can see strain. So here you can see a strain event measured just after deployment. And then 2 months after, the strain event had transformed itself in break. So there were only 450 meters left into the well. So it has been used, let's say, as a draft for a second descent. So we decided to do something much more simple with one single wireline FO cable, meaning it's like this. So you have 3 fibers inside the fiber and metal tube, and with a lot of reinforcement, allowing the cable to be, let's say, self-consistent, meaning you will deploy this cable point in just the cable with a load at the bottom. And then this has been successfully deployed along the wall depths of the well, so 2,200 meters in September 2020. And then first result and first thing we have done is a DTS measurement. So it's the blue curve here, Raman DTS. And you can see the overlap between this blue curve, which is acquired just after deployment by Febus Optics, and the orange curve, which comes from previously logged data by AS in the 90s. So you can see first the accuracy of both measurements, which are overlapping perfectly. Here, this here is due to the ambient temperature differences between the 2 measurements, which were at some decades of difference. But you can see here a perfect match. So it means the cable has been successfully deployed. Then in parallel, actions to study the aging of the cable, because it's one of the topics of Febus in this project. So we have put this cable in a geothermal bath here, 6 months, and performed aging test with, let's say, tension, traction test on the cable, and monitoring all along the 6 months, and after traction, of course, the optical losses. And we have seen no variation, meaning that there is no damage on the cable, at least on lab condition, without the temperature and without the constant traction we can have on the real wire line. So now our next actions on this well EPS1 will be to do temperature and acoustic measurement to track induced microseismics during the ORC startup, which is scheduled actually next week. And today, Febus specialists are currently on site at Soulsous-Forêt to prepare this test. And thank you very much for your kind attention. And if you have some questions, I don't know if we have time. Xavier and Christophe.
Okay. Well, we have one question. So the first, thank you for your interesting talk. Okay, so the question is from Benoit Vallée. What is the competitive advantage of Febus Optic compared to many other fiber optics based sensing company?
Oh, it's a very commercial question.
Yeah.
So I will go to some slide. I actually skipped the slide, but let's say the main advantage of Febus Optics is to have in-house technologies such as Brillouin, Raman, and Rayleigh acoustics. So we are mastering all the technologies, meaning that if we have advice to give to a customer, we can do it without any bias, let's say, because we can provide all the technologies. So this is one advantage. Let's say the second advantage we have, and it's mostly for universities, it makes sense, is we can give you full support from the device. We can sell the device and then give you full support to choose a cable, but with a partner, we are not providing our cable. We can do it, but it will be commercially available cable, and you can we can give full support without hiding anything. We can give you the raw data. We can explain you everything from top to bottom, how it works. Maybe as I have done today, but even deeper on any device, because our business model is to give the best device, not to sell service.
Okay, thank you, Vincent. And the question from Enzo: what is the frequency range for sampling?
You mean for DAS?
I suppose.
Yeah. So it's 10⁻³ hertz, so 1 millihertz, and the upper limit will depend on the length of the fiber. Barely, if you take a 10-kilometer long fiber, the limit will be 5 kilohertz Nyquist. So 10 kilohertz sampling and 5 kilohertz Nyquist.
Okay, another question from Bertrand Maillot. Is there any way to retrieve information on ambient stress from the strain measurement?
Ambient stress. What's ambient stress?
The stress in the formation around.
Oh yes. You mean static stress?
Static stress in that case, I suppose, yes.
Yeah, the variation on the static stress, maybe you can have access to using Brillouin or using Brillouin and a couple cable. You have to cement a cable into the formation on the axis you want to measure the strain. This can be done, but if you want the absolute stress, strain, it's not directly measurable. Maybe it can be done by a process. I don't know, but yeah, maybe it can be done. But you know, I'm only the tool provider here.
In fact, you measure strain rate or
strain. We can measure
strain, but
yeah, with Brillouin,
variation.
Yeah, but it's still strain between the first measurement and any other measurement. Brillouin. You cannot have, the only absolute value of strain you can have access to is the one of the fiber inside the cable. So it's dependent on the manufacturing of the cable, not the formation.
Okay, another one, I know the answer, but I'll let you answer. Can you measure strain perpendicular to the cable?
We are a bit sensitive. Strain or strain rate?
Strain.
Strain, but static or strain, let's say at certain frequency. Static, no. Actually, the problem is we cannot differentiate this strain from a strain coming from the axis of the fiber. If you want to separate the effect, we will need to have some kind of helicoidal shaped fiber.
Yes.
And straight fiber, but there is an effect. There is a orthogonal effect on the fiber, but it is weak, and it is let's say lying into the other actual effects. So it's not visible.
Yes. Okay. So after that, helicoidal cable can be a solution. Yeah.
Yeah, but you have to use helicoidal and straight if you want.
Yes, of course, to make the difference.
Yeah, on the helicoidal cable, except if the helica is 20 meter. It's a cable of 20 meter outside diameter. So if it is a small cable, let's say 2 centimeter outside diameter cable, then you will have a sensitivity to transverse waves, but it will be mixed with axial waves. So if you have an axial cable, then you can see the effect on one and on the other and try to do something to separate.
But the point is that you have no information about direction,
No,
azimuth.
No.
Yes. So
And the same,
it's partial information.
Yeah. And even on the axis, the difference between DAS and
geophones,
for example, is you don't know where the signal, if the signal comes from the top or the bottom. It's very straight, meaning that you can see it with propagation, but you have no polarization. That's what I mean.
Yeah.
You cannot. It's not like something you're not measuring displacement actually.
Yes.
It's not displacement on the right or on the left. It's expansion or contraction.
Okay, that's clear. Another question from Armand: Does the optical fiber is able to stay in a geothermal well for decades?
Yeah, this is one of the question we are trying to answer on the MID project. Inside the water, I won't bet, but cemented outside the casing, I think yes, because it has been tested on nuclear power plants into the concrete, embedded into the concrete, and it was from let's say early 2000, so it's 20 years. So it survived 20 years. So we can say it's at least 20 years cemented.
Okay, so interesting tool for permanent monitoring.
Yes.
During
but
a long
for
time.
wireline, yeah, you cannot. The wireline has been put in for example, the wireline has been deployed in September, last September. Now we will need to remove it because it will start to be risky at some time. That's why we have done some aging surveys in parallel. But even at the end, the conditions are not exactly the same, and the wireline is not planned to stay forever inside the well. Let's say 1 year should be a good limit.
Okay, another question from Jérôme. Have you deployed these systems in horizontal geothermal producers to detect zone of high influx?
No, I would like to do it, but I didn't have the chance to do it.
Okay. Another, the last one probably. Have you deployed this system in geothermal injectors to monitor flow distribution and monitor the potential risk of out-of-zone injection?
No. No. To be honest, no in geothermal wells.
And the last one, I hope, yeah. Have you or not deployed these in the cemented liner?
Cemented liner, meaning a liner inside which will be cemented. So I don't know this type of completion. We have deployed in cemented casing, so meaning outside the casing.
Yeah.
Yeah, I would say it's quite the same. I don't know. The liner it's something you put afterwards inside the casing and then cement it, or how it works.
Sorry, I cannot answer for that point. I don't know as well what is a cemented
maybe
liner. So if, but we can say, I can just add a few things that typically we have the between casing and the formation in the cement. So this is always a very good coupling.
Yes.
And then you may have attached to the tube, which is a tube production, for example, and we name that on tubing. And sometimes also it is just put like this. And when you have deviated wells, then the weight of the cable is sufficient to couple it to the casing. It's a partial coupling, but it's sufficient.
And you may want to put some slack on it in order to maximize this coupling between the wire line and the well.
Okay, So I have no precision about cemented liner. So we will finish question
Yeah,
now.
but if
So
you want to be in contact with me by email, don't hesitate.
yes,
And
of course.
I will try to be as accurate as I can.
Okay. Okay, so thank you for all your questions. And thank you again for this very interesting talk, Vincent. And the second part of the geothermal winter school being finished, would like, thanks again all the speakers for their contributions and the audience for the questions.